interest here. What do we provide our clients with? This is mean loading, so the drag force, essentially, that acts on the building. This is the peak static or the gust loading, the addition that is due to the turbulence present in the natural wind. You know, these buildings are built in cities, and the cities are very turbulent. So the increase in loading is significant. If we have a very flexible structures, we also needed to include the effect of the building moving in the wind. That is very important. Sergio discussed, Engineer Sergio Stolovas made the point that a crosswind loading, or the loading that is generated perpendicular to the flow of the wind, is key to the design and is not addressed very well by the code. And you can see it here, if I can manage. You know, mean load is 0, so this means that for this wind angle we have a completely a crosswind response, and you can see that you have almost a maximum loading because and this phenomena is called vortex shedding, and I believe Sergio already discussed it. We also provide for tall building, it's important, occupant comfort. These two videos are very old. One of the lady was one of my ex-colleagues. She worked for many years at Melissa Barton. She worked for many years at the University of Hong Kong, where they have this amazing room where you can simulate the motion of a building. This is 30 milli-G is a building that has some problems, but depending on how flexible is the structure, 0.25 hertz, it would be your typical 200 meters tall building in Balneario, for instance. 1 hertz is a very stiff structure, but still, the 200-meter building, 30 milli-G, you feel it when you have a storm. So it's important that these quantities are derived accurately by wind specialists, because you cannot, you design a building with this problem, what do you do? It's unlivable. But when we do these wind tunnel studies, we always adopt synoptic profiles, whether the climate is mixed or it is dominated by thunderstorms. These 3 graphs show the target profile, so what we derive via the code or our methodologies. This is the mean wind speed profile, variation with height, turbulence intensity, with obviously decreases with height, and this is the gust loading, a combination of these two. And the dots are the measurements that we have taken in the wind tunnel. Obviously, when we set up an experiment, we need to simulate correctly the local wind speeds that the building would experience. Whichever climate you have, whether it's driven or not by thunderstorm, these are always the same profiles. We never simulate a thunderstorm profile. Why? Because we don't know how to do it. It's as simple as that. So what happens when we are in one of these cases? So we need to derive wind loading on a tall building in a thunderstorm-dominated region. I'll explain it via a case study because it's much easier. I'll try to be quick because I only have 10 minutes left. This is a 165 meters tall building, base dimensions at 20 by 30, so it's extremely slender. The surround is only low-rise. I have chosen this particular building because the client was very supportive, and also because you can really see in the loading just the effect of the tower without the added complexity of the surround. All the wind tunnel studies were done, it's a commercial project, all the wind tunnel studies were done at the University of Geneva. We have already discussed about the model. We used a pressure model. This is what it looks like inside. It's full of tubes. Each tube corresponds to a pressure sensor. In this case, we use the scale of 1 to 400, 350 pressure sensors, and we did the test every 10 degrees, a full set of wind directions. And all the tests were conducted using a synoptic profile, because that is what the code tells you to do, and we cannot be imaginative. These are the results. From the test, we obtain overall base loads for foundation design, floor-by-floor loads for the design of the core, peak accelerations for comfort assessment, I have the video, and also cladding pressures. And these is the variation of the wind loading. This is the the moment, the MZ, and here you have the FX and the FY, and these are the data that essentially we provide to the designers. But Project X is located in a very unlucky climate. The design wind speeds were derived based on EVA's statistical analysis of the weather data at the nearest weather stations, several airports, because we want to make sure there is consistency. The 50-year return period mixed climate wind speed is 45.6, which is the one we need to use to design, 50 years. The synoptic wind speed, this is an extreme case, is very low, it's only 33, it's here. And the thunderstorm speed is obviously 45.6, it drives the design. So, in a nutshell, what I'm saying, what I want to show you is the difference in loading. This graph shows wind direction, and I've picked one of the forces. The black line shows the peak static, so the loading essentially due to turbulence. I'm ignoring the contribution of the stiffness or the flexibility of the building. For the mixed climate, the 45.6 meters per second, so it's the design wind speed. Now, if we should be able to ignore thunderstorms, we could be designing for this. And you can immediately see that it's almost half of the loads. You know, the ratio is almost 2. What happens when we add the dynamic? Again, this is an extreme case because unfortunately for this case, we had this vortex shedding across wind phenomena that exacerbated the situation significantly because for higher wind speed, this phenomena of vortex shedding was much stronger. So ultimately, we had to tell the client to design the structures for loads that are 2.5 higher than those that we believe are the real loading. This is, and Sergio already spoke about vortex shedding. This is the vortex shedding on this tower. You can maybe see the vortices detaching and pushing the tower sideways. And this is because we have the significant increase in load. Now, thinking inside the box is a very English way of trying to say that if we don't challenge ourselves, we will never get better. Unfortunately, as engineers, we can try to challenge ourselves and say, okay, what we are doing here is silly because we have these loads that are 2.5 higher than what we think they would be in real life because thunderstorms are not important. But we have constraints, and in this case, the biggest constraint is certainly the code, because we need to follow the code as engineers. But it's also time. If we should have a lot of time, we could design a better structure. So we don't want to think inside the box, we want to think outside the box. And as I said, the collaboration between us and Sergio, the University of Genoa, and the client led to the decision of starting a research project, because we want to try to not understand. We believe that thunderstorms are not important, but the fact that I personally believe or professionally believe that thunderstorm is not important is absolutely irrelevant. We need to be able to prove it to ourselves, and we need to be able to find a way to codify an approach to deal with thunderstorms. So we were thinking outside the box, and we started asking ourselves, can we qualitatively assess if a thunderstorm is really important for the design with the tools that we have? What happens if we split synoptic events and thunderstorm events, and we model them as appropriately as we can with the tools we have? And can we reliably model a thunderstorm profile in a traditional wind tunnel? There are many types of wind tunnel. For a traditional wind tunnel, I mean a wind tunnel that is used by all the wind engineering consultancies in the world, which is an atmospheric boundary layer wind tunnel. That's when our research project started, and first thing we did, looked at the climate, looked at the profile of the wind speeds. These graphs shows the target synoptic profile. This we are certain of because we derive it from the code. And then these 4 lines are 4 possible thunderstorm profiles with the maximum wind speeds at different height, 180, 120, 80 meters, 40 meters, and 20 meters. There is a lot of variation. Unfortunately, this is the state in which the thunderstorm research is at the moment. There is uncertainty over how the profile looks like, and where is, most importantly, where is the height of this maximum. Obviously, the height of this maxima will vary. It will be different maybe in Brazil near the coast, or in Brazil inland, and will be different in Italy. The same happens for synoptic events. They are not all the same in the world, and they change depending on the location where you want to calculate your profile. But we know how to do so for synoptic profiles, but we don't know how we would do that for thunderstorm profiles. So there are many formulations to estimate a thunderstorm wind profile. And we had to make some assumptions. So what we wanted to do as an initial part of our research, then became a much bigger project, was to say, let's try to do something better and see if what we believe, so that thunderstorms are not important, is if we can somehow prove it to ourselves. We made a choice. We decided to model, we have this synoptic profile. We decided to model this thunderstorm profile with a nose height of 80 meters. There are many formulas that are available to define a thunderstorm profile. These formulas are derived by scientists based on full-scale measurements. Different scientists would provide a different formula. Our favorite is the one from Kenny Kwok. Kwok and Wood provide a reference there, and it is our, what is not our favorite, it's actually my favorite because it's the simplest one, but it's also the most reliable based on full-scale measurements. So this formula was written a long time ago. The paper was published in 1998, but if you compare this empirical formula with measurements that have been taken all over the world, it seems to be one of the best. Then turbulence is very important, because we know that the wind loading on tall building is driven by the mean loads, by the average wind, but also the level of turbulence. Here we really struggled, despite the fact that this research project was done together with the University of Genoa. We found that there is not much in literature available in terms of the level of turbulence that are expected to occur during a thunderstorm. 7% is the value that we took based on extensive literature research. And I failed to say before that we have a PhD student together with many other people that are working full-time on this now. This is how the wind tunnel looked like. This was a research project in itself. How do we set up a thunderstorm profile in a standard boundary layer wind tunnel? Completely different, a bit different from what you would do for a synoptic profile. This is a fence this you would have for a synoptic profile, and all this cube which simulate the roughness, the rugosity of the ground. But we also had to add this grid. You see just one picture, but we went through something like 40 iterations. It's a partial grid that essentially slows the wind down at higher levels, and the model would sit here. So these are the results. With these assumptions, we repeated the test on the same Project X tower, and this is the mean load. This is the mixed climate, so the design, and this is the thunderstorm only. What happens if we consider a thunderstorm profile instead of a synoptic profile? The difference in the maximum loads is around 3. Why? This is why, because the load, something happened in the picture, sorry, but I'm sure you get what I mean. The strength of the thunderstorm profile decreases significantly with height, and loads vary with the square of the speed. So it's obviously very clear that this profile, the synoptic profile, would dominate. Wind speeds are the same here, but then the thunderstorm one decreases, and therefore the overall load is much lower. When we introduce the effect of turbulence, it's even worse or even better, depending on the way you want to think about it. The ratio between the design loads that we are forced to use if we follow the code and what we think are more or less the real loads is about 4. We introduce the dynamic, the ratio is 7. What does that mean? The initial result of our R&D study implies that we should continue our research for sure, as in the future we might be able to design for these much lower synoptic profile, and we might be able to neglect thunderstorms when designing a tall building. So can we, as engineers, apply now this method in design? No, because it's not codified. So we cannot, we can gather information, but certainly we cannot design a building using simulating a thunderstorm profile in a traditional boundary layer wind tunnel. So what do we need to, that's why I'm saying in the next 2 points that our study has limitation. It was just an initial study done last year. We don't know enough about thunderstorm, and we need to continue our research. We will continue, we have decided that as a team, to research this phenomena, to understand how we can best model thunderstorm in a traditional wind tunnel. Why I keep on saying a traditional wind tunnel? Because there are wind tunnels that simulate thunderstorms, but they are extremely expensive. I'll be very quick. Now we are trying now, as part of the research project, to access facilities that are purposely built to simulate thunderstorms, and obviously full-scale monitoring will be advancing us and allowing us to make a real step forward. We published a paper a month ago exactly on this topic, the experimental simulation of thunderstorm profile in a traditional boundary layer wind tunnel. It's the first paper on this topic. Now, special wind tunnel is the next step. We are trying to access these facilities. In particular, we are trying to gather fundings from the European community to do so, because these facilities are extremely expensive. Wind tunnels that can simulate thunderstorms are very rare, and they are generally research facilities. These pictures that I'm showing you here is the Windy Dome, one of my favorite thunderstorm facilities, and is in Canada. And this is what happened when they simulate a thunderstorm. There is a jet of air that comes from the top. It's exactly the same as it happens in real life. What we want to do essentially is take our model and put it there and measure the thunderstorm loading. Full-scale monitor will be of great importance. We have now an agreement with the owner of Project X, and as soon as Project X will be completed, obviously within 6 to 8 months, we'll be able to instrument it. That will give us some invaluable data, because we will be able to compare, if we are able to stay there for long enough, the acceleration due to synoptic events with the acceleration due to thunderstorm events. And I believe that we will find that every time the building is experiencing a thunderstorm, it's not moving. And these are, more slides on the monitoring. So the conclusions are that all buildings in the mixed climate regions or thunderstorm-dominated regions are likely to be significantly over-designed. Thunderstorm events are a research phenomena, as you can see, despite the fact that many organizations and universities are putting an incredible effort in doing so. They're simply very complex. And this prevents engineers from carrying out detailed studies and accurate assessments of their effects in design. We need to research more collectively, both as universities and also commercial organizations, because we need to direct, I think, the research of the university towards what is needed by the engineering world. So we need to work together. The local effects of thunderstorm of cladding should be investigated further, as cladding elements could be severely under-designed in these climates. A few words of thanks. It's a big team. I have the honor to be presenting here, but I'm speaking on behalf of many people at UNIGE. I had a lot of people helping me in this research, and especially Camila, which is a lovely student from Cuba, is our PhD student for the next 3 years, and I'm sure she'll help us very much in in advancing this research. And then I want to thank Professor Giuseppe Picardo, because he allowed us to use, as soon as we found that we had this problem with Project X, he allowed us to use the facility for free at the University of Genova, didn't put any limits. And muito obrigada. Thank you. Oh, thank you, sorry.
Bom, vamos abrir para perguntas, então. Alguém tem pergunta? Só levantar a mão. O microfone vai até vocês aí. Ninguém? O professor Carrazedo não está aí para fazer a pergunta lá da parte da manhã?
I don't know. I think I know already what I want to ask. I already know the answer. No?
Microfone lá na porta, por favor.
I don't know what I have it.
Boa tarde, professor Ricardo Carrazedo, da Escola de Engenharia de São Carlos. Parabéns pela apresentação. Eu queria, como sugestão já do Stolovas, né, te perguntar a respeito do uso das ferramentas de simulação computacional, né? Que podem incluir o fluido e a estrutura, né, e possibilitar visualizar, né, essa interação, e como essas técnicas hoje representam o que é obtido em túnel de vento, né? Qual a proximidade dessas simulações e como vocês consideram atualmente como um possível complemento para os resultados que podem ser obtidos experimentalmente. Obrigado.
Okay, it's a very interesting question and it's extremely difficult questions, and you ask probably 10 or 20 wind engineers and they'll give you different answers depending on whether they have a wind tunnel or not, to be brutally honest. We have a CFD group, so we do CFD. But we use it only for wind comfort, and for wind comfort, not only for wind comfort, we use it for many applications, but certainly not for wind loading. It's simply not quite there, the technology. I still have to find a scientific paper. For a start, even the code doesn't allow you to use a CFD. If you have the opportunity, download the City of London guidelines, which are very clear about the use of CFD, even for simple things like wind comfort. Wind comfort is something that we don't do very much in Brazil, but essentially in London or in UK, we do a lot of it. Every time a new building is built in Brazil, what needs to be done is that a series of studies to understand that the wind speeds at the ground level near the new development are not worse than what they were without the new development. So essentially we measure wind speed in the wind tunnel. For these studies, we do use CFD. We do use it as even a combined tools. Sometimes the wind tunnel can or cannot be more expensive, but sometimes if the wind tunnel is busy. For instance, now we have a project where we are using a combination because we have facility time is very difficult to find, while the computer is always available. So we would do CFD studies to inform and help us when we do the wind tunnel studies. But this is for just for comfort. We are doing a lot of exhaust modeling, fumes modeling for using numerical simulation. We are not doing wind loading because it's not quite there. However, we are very interested in the research. Our CFD team is applying for a research grant to study especially this. So they try to find a better way to derive wind loads based on CFD. And obviously there is going to be a lot of comparison with the wind tunnel. It's simply not quite there, the technology. The results are often very different, and as Sergio was saying before, and that is also my experience. When we provide the CFD team with the answer, and I never do that, I'm very, very careful when we do research projects. I don't want to give them the answer because they can always match them. But if you don't give them the answer from the wind tunnel, then they end up having different results. But we are trying. I've done recently a CFD study with the WSP. When we did some WSP London, some simulations to understand the movement of a bridge in the wind with CFD, and then we wanted to see the match with the wind tunnel. That was not good at all. And that is my experience also of doing some other bridges with other very famous designers in the world. But we needed to work on it. But I don't think for many years we will still need wind tunnels. That's my opinion. But it will be different if you consult somebody that is doing CFD. It would tell you that you can do it. You need to be very careful because the code doesn't allow you to do so yet, to use CFD as a tool.
Thank you, Ana. Mais alguém? Não? Então, I thank you so much, Ana. Really appreciate that. Thank you so much.
Thank you.
Thank you.
Thanks a lot for everyone.
Yes. Agora vamos para a última apresentação do dia. Engenheiro Fatih Riones, da WSP de Nova York. Fatih é vice-presidente sênior da WSP em Nova York e é um dos responsáveis aí pela concepção e análise dos edifícios mais altos e esbeltos do mundo, entre eles o One World Trade Center, 432 Park Avenue, 111 West 57th Street, entre outros, né? E vai falar um pouco para a gente sobre a sua experiência aí no projeto dessas torres super altas. Então, Fatih, please. Okay, clicker, move forward, back, laser pointer. Okay, you just need this trick. Okay.
Be good. That's another good start.
Só um segundo, a gente está resolvendo um
Okay.
probleminha técnico aqui com o retorno. Pronto.
I think we get right.
Ok, acho que tá indo.
Okay, thank you. Thank you, Douglas, and I would like to start my presentation thanking IBRACON to give me and my company the opportunity to be here. We're very happy to be the part of this talk and with the other distinguished speakers. I would like to introduce myself quickly. I'm a Senior Vice President in WSP New York. I'm also Director of Analysis Group. My specialty is high-rise structures and special structures, not necessarily very tall buildings and very special structures, including stadiums and other structures. A few things about WSP. WSP is a global engineering company. Roughly, it's over 40 countries with close to 48,000 engineers. We don't only provide engineering for structural engineering. We also provide engineering for environmental, mechanical, lighting, and a few other, especially our infrastructure group is very big. These are some numbers from our this marketing team, so I'm just going to skip this. So New York office is basically focused on high-rise structures, and I would like to show you a few structures that we've been part of, developed, to give you an idea what kind of structures we've been working with and what kind of experience we have been in.